In the early 1960s, Phil Anderson, while he was at Bell Laboratories, published a fundamental paper. In hindsight, it's becoming clear just how fundamental it was. He was working in solid-state physics, and he noticed that there was some amazing parallels between the theories of solid-state physics and those of particle physics, that at a very low level, clearly particle physics encompasses everything, but at a very high level, solid-state physics is what we see. We see materials all around us, not atoms. And so he looked at this and he realized that in both cases, in particle physics and in solid-state physics, there was a scalar quantity. In particle physics, this came to be called the Higgs boson. In solid-state physics, it was simply a scalar that multiplied everything, that gave everything what's going on. So, for example, if I have, say, an electron and a proton, they're each multiplied by the same scalar, but the mass of the two is very different. So the end result is, if the scalar is 0, they have identical masses. They have no mass. But when the Higgs boson, the scalar quantity, is not 0, then we end up having the ratio of the masses being on the order of thousands to 1. And the same thing is true in solid-state physics. And this was picked up by Peter Higgs, looking at what Phil Anderson had done, and so it goes. It's not surprising that in the late 1970s, Phil Anderson was awarded the Nobel Prize in Physics for theory. And rest assured, to get a prize in theory in physics, you need to do some amazing things.